We're going to finish chapter 8 with 8.3. We're not going to be covering 8.4. And we're going to be testing a claim about a mean. So essentially, it's going to be the same hypothesis testing procedure that we've seen before, but there's two situations that could happen. The standard deviation sigma is not known, which is very common. We're mostly going to deal with that, and then when sigma is known. So we'll be focusing our main attention here, and then just one quick example for the latter because, oops, that should say known, because usually sigma is unknown. So the procedure is the same, and the only difference is that our test statistic is going to be a little bit different, so we'll be using a different calculator stroke to figure that out. We're still going to love the p-value method over the critical value method, but we'll still do both. We're still going to have the same wording for the final conclusion. So when we test a claim about a population mean when sigma is not known, this is the notation we'll be using. And there's two requirements. It's got to be simple random, the population needs to be normally distributed, or the number of trials needs to be greater than 30. So for a test statistic and p-value, for testing a claim about a mean, the test statistic is going to be using t-test. Now, the majority of the time we're going to be using t-test, but if you happen to know sigma, you would use z-test. But for the majority, we're going to be using t-test. And that is going to give us the test statistic and our p-value. Now, just a reminder, when we're talking about t-distribution, we're talking about the degrees of freedom, which is n-1. Now, if we are going to use the critical value method, then we need to find the critical value t. And this is a reminder of how we found critical values in the past. We would go to second VARS, so we're going to the distributions. We're going to go to INVT, and we're going to go to the area, the probability to the left, and we need the degrees of freedom. So this is how we would, if we use the critical value method, this is how we would need to go one step further to figure out the critical value of t. So the author obtained times of sleep for randomly selected adult subjects, and they're listed below, and they are normally distributed, ding, 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 for requirements. A common recommendation is that adults should sleep between 7 and 8 hours each night. Use the p-value method with the significance level of 0.05 to test the claim that the mean amount of sleep for adults is less than 7 hours. So our claim is that the mean is less than 7. So let's look at our null and our alternative. Our claim needs to go down here because it doesn't have equality. So our null hypothesis would be that it would be equal to 7. So now we'll go into our stat. And this time when we go to test, we're going to go to t-test because we don't know sigma. So we're going to input the stats here. Our our null is 7. And our x bar is 6.83. Our sample standard deviation is 1.99. And our n is 12. And our symbol is less than. So that will stay the same, what's already highlighted, and we'll calculate. So if we're doing the p-value method, our p-value is 0.386. And so is it less than or equal to our significance level? It is not. So we would fail to reject the null hypothesis. And we would go to our table to help us remember how to do it. Our original claim did not include equality. And we failed to reject, so we would use this language here. And so we conclude there is not sufficient evidence to support the claim that the mean amount of adult sleep is less than 7 hours. Go ahead and give this one a try. Press play when you're ready to see the solution. And let's do another example. So in this data here, they give us our summary statistics. They give us a different significance level, and they want us to test the claim of a seismologist that these earthquakes are from a population with a mean equal to 5. So our claim is that the mean is equal to 5. So they want us to use the critical value method. So it has equality, so our claim is the null hypothesis, and so this would be not equal to 5. And so we still run the same statistics, but this time we need our test statistic, and so that we can test that value and see if it's in the critical region. So we're going to go over to our t-test, and we're talking about 5 this time. Our x bar is 5.82. Our sample standard deviation is 4.93, and we have 600 to go from. And this says not equal to. So let's go ahead and calculate it. And our test statistic is 4.07. And so now we have to do the critical value method, which is first we need to decide what type of tail this is. Because it's a not equal to, this is a two-tailed test. And the thing about a two-tailed test is we actually have to divide our significance value into 2 to cover that space. So our significance value in total is 0.01, but this region is 0.01 divided by 2, and this region is 0.01 divided by 2. And so these two different critical t values here are going to tell us if our t-test is in, our test statistic is in those critical regions. So we will use our calculator to figure this out. So we will go to second VARS, and we want INVT, and we want the area 1 minus, and you can do 0.01. Let's look at this for a second. This region here is going to have 1 minus that, but let's just calculate this region here. And because there's symmetry, whatever we get will be the positive and the negative. So we'll just do 0.01 divided by 2. So, ooh, too slow. It kicked me out, I guess. Let's go back here. So we're going to do 0.01 divided by 2. And the degrees of freedom is 599 because it's 600 minus 1. And so we get the critical value is negative 2.58. Which means this critical value is symmetrical 2.58. So now where does our test value fall in this region? Well, it's going to be 4. It's all the way over here. So we are definitely going to reject the null hypothesis. And so we would go through and we would pick, our claim did have equality. We rejected the null hypothesis, so we're going to stay. There is sufficient evidence to warrant rejection of the claim that the population of earthquake depths has a mean equal to 5. Go ahead and give this one a try. And you are going to use the critical value method just for practice. And there's the solution. And we'll do one more together. And then one more, and then we'll do sigma no. So they give us this data here, and they don't tell us how to test it, so we can do whatever we want. So hint, we're going to do the p-value. But so the claim here is that the mean temperature is equal to 98.6. So that is going to be our null, because it has equality, and so not equal. And this is our claim. So let's go ahead and grab our stat. We're going to do a t-test because we still don't know sigma. And we're talking about 98.6 degrees. Our sample mean is 98.2. Our sample standard deviation is 0.62. We have 106. And we've got not equal to. So our p-value is 1.40 E. Now don't miss that E, -9. That means it's really, really small. It's 0.00000. So essentially our p-value is 0.0000. Is that less than or equal to 0.05? Yeah, we are going to reject the null hypothesis here. And so that means how we'll interpret that if we go to the table. There is sufficient evidence to warrant rejection of the common belief that the population mean is 98.6. Go ahead and give this one a try. You can use whichever method you like. And there's the solution. And finally, the only difference to everything we just did is if the sigma is known, instead of clicking t-test, you're going to click z-test because you know the sigma. And you can see right there, it says that it asks for the sigma. And that's the only difference between knowing the sigma and not knowing the sigma. And that concludes section 8.3.